Welcome to the vSAN 6.0 architecture module. This module describes the architecture, objects, and components of vSAN 6.0. This module also explains how vSAN 6.0 captures snapshots and clones. This module then explains the traffic flow pattern and fault domains of the vSAN 6.0. Click Next to continue. At the end of this module, you will be able to describe the architecture of the vSAN 6.0, identify the objects and components of the vSAN 6.0, explain snapshots, clones, traffic flow pattern, and fault domain of vSAN 6.0. vSAN is a cluster-level feature that is integrated with VMware ESXi to create a distributed redundant array of independent disks, or RAID. To configure a vSAN, a group of ESXi hosts are grouped into a vSphere cluster. vSAN then combines storage capabilities dispersed across multiple hosts within each cluster and present them as a single storage cluster resource. A vSAN cluster can also contain hosts that do not have any storage capacity. However, at least 3 ESXi hosts in the vSAN cluster must contribute local storage to the vSAN Datastore, and this local storage must be a combination of one solid-state disk, or SSD, and one or more hard disk drives, or HDDs. The nodes communicate with each other through a specialized vSAN network. vSAN uses a combination of flash-based devices on ESXi hosts and magnetic disks to store data. It uses the Ethernet network to replicate data between ESXi cluster nodes according to the configurable policies. Magnetic disks provide the overall storage capacity in the persistent data storage tier. In hybrid architecture, flash-based devices provide a cache tier for the virtual machines. Moreover, in all-flash architecture, flash-based devices are used for providing cache and capacity tiers. Disk groups are vSAN management constructs that are composed of cache and capacity devices. vSAN hybrid disk group configurations are composed of at least one cache device, such as PCIe, and one capacity device, such as HDD. The cache devices are used for read caching and write buffering, while the capacity devices are used for storage capacity. In the hybrid architecture, disk groups cannot be created without a cache device. vSAN all-flash disk group configurations are composed of at least one performance flash device and one capacity flash device. The flash devices are used in a two-tier format for caching and capacity, while the capacity flash devices are used for storage capacity similar to magnetic disks. In the all-flash architecture, disk groups cannot be created without a capacity flash device. vSAN 6.0 allows users to manage an externally connected disk enclosures, or just a bunch of disks, or JBODs, and leverage the existing investment in blade-based architectures. This enables vSAN to scale on-blade servers by adding more storage with few or no local disks. vSAN 6.0 also provides flash acceleration on the server or in the external subsystem. The platforms on which this capability is currently supported are IBM Flex 10 with X240 blade series, Dell FX2 with 12G controllers. vSAN 6.0 includes a new on-disk format-based file system that delivers higher performance, scalable snapshots and clones, and online migration using Ruby vSphere Console, or RVC. The object store of vSAN 6.0 mounts the volumes from all hosts in a cluster and presents them as a single shared data store. It is to be noted that the upgrade to the new on-disk format is optional. The on-disk format for vSAN 5.5 will continue to be supported. Administrators can determine the disk format in the UI by identifying the file system as either V1 or V2. While V1 represents the earlier version of Virtual SAN, V2 represents Virtual SAN 6.0. The Virtual SAN Datastore is an object store solution that is created using disk groups from the hosts in a cluster. The disk groups of all ESXi hosts in a Virtual SAN cluster are combined to create a Virtual SAN Datastore. The size of a Virtual SAN Datastore is governed by the number of HDDs per ESXi host and the number of ESXi hosts in the cluster. For example, if each host has 2 terabytes HDD and there are 3 hosts in the cluster, the raw capacity of the Virtual SAN Datastore is 6 terabytes. The Virtual SAN Datastore is used to store virtual machine files, including the virtual machine disks or VMDKs. The Virtual SAN Datastore is only accessible by hosts that are members of a cluster, which is enabled by Virtual SAN. The Virtual SAN Datastore cannot be presented to external hosts, but its capacity can be exposed externally through third-party integration solutions. Remote data stores such as the Logical Number Unit, or LUN, and Network File System, or NFS, can be presented to hosts that are members of the Virtual SAN cluster. Hosts in the Virtual SAN cluster do not need to be identical. Even the hosts that have no local disks can participate and run their virtual machines on the Virtual SAN Datastore. Virtual SAN stores and manages data as flexible data containers called objects. The Object Store file system manages data as objects. Each object includes its own data, part of the metadata, and a unique ID. By using this unique ID, the object can be globally addressed by more than the file name and path. The use of objects allows for a detailed level of configuration on the object level. For example, RAID type or disk usage at a level higher than the physical disk blocks. In a block-level file system, blocks are arranged in a RAID set or logical disk first, and the file system is created on top of the RAID set. The file system includes the metadata or file allocation table that defines file names, paths, and data location. In this environment, the file blocks are laid out on the disk according to the file system structure, and the data protection is based on the RAID set. An object is a VMDK file, a snapshot, or the virtual machine home folder that is namespace. Objects are logical volumes with data and metadata distributed and accessed across the entire cluster. A single Virtual SAN cluster can store and manage tens of thousands of objects. Virtual machine objects include multiple components that are distributed across disk groups on ESXi hosts. The distribution is based on the requirements defined in a virtual machine storage policy and internal optimization routines. These components can be replicated or striped to enhance availability and performance capabilities. When you provision a virtual machine on a Virtual SAN Datastore, Virtual SAN creates an object for each virtual disk. It also creates a container object that stores all the metadata files of the virtual machine. All virtual machine files, excluding VMDK's Delta files and the swap, reside in this home directory on the Virtual SAN Datastore. Virtual machines have 5 different types of objects. They are VM Home, VMDK, VM Swap, Snapshot, Memory. Click each type to learn more. VM Home stores all the virtual machine configuration files. VMDK is the virtual machine disk file. VM Swap is created when virtual machines are powered on to serve as a backing store for the virtual machine's RAM contents. By default, the swap file is stored in the same location as the virtual machine's configuration file. Snapshots are created when snapshots of the virtual machine are taken. They are the differential changes between the parent snapshot and any other snapshot taken at a given point in time. Only the differential from the parent snapshot is preserved every time a snapshot is requested, instead of a full snapshot of the disk. Storing the snapshot delta saves storage. Memory, or vMem, backs up the guest main memory on the host file system. This file exists only when the virtual machine is running, or if the virtual machine has crashed. Virtual machine objects are split into multiple components based on performance and availability requirements defined in Virtual Machine Storage Profile. Objects are comprised of components that are distributed across hosts in vSphere cluster. Each storage object is deployed in Virtual SAN as a RAID tree, and each leaf of the RAID tree is a component. The caching and buffering capacity for the components are provided by the flash-based devices. They are transparently assigned with their data stored on the magnetic disks. The objects that are larger than 255 gigabytes in capacity or larger than the capacity of physical media are automatically divided into multiple components. Virtual SAN 6.0 currently supports a maximum of 9,000 components per host. Virtual SAN uses a virtual machine storage-based distributed RAID architecture to distribute object components across multiple hosts and disk groups. It abstracts and aggregates the local storage of the host and creates a distributed RAID. In Virtual SAN, performance and availability requirements are implemented as predefined policies on every object. Virtual machines and individual VMDK files can have a storage profile associated with them. Each object has its own RAID tree that converts the policy-defined performance and availability requirements into an actual layout on physical devices of the Virtual SAN data store. The objects are stored based on techniques such as mirroring and striping. By default, Virtual SAN does not keep a copy of the VMDK on the host where the virtual machines run. Instead, Virtual SAN decides how to configure and lay out the object across the cluster based on overall optimization goals. In Virtual SAN, each object is a logical volume with data and metadata. They are distributed and accessed across hosts that are the members of a cluster. Such objects are also striped into multiple components due to capacity constraints, or when a component size reaches 255 gigabytes. These objects and components are distributed and stored in distinctive combinations of disk groups within the Virtual SAN data store. This distribution forms the layout of the objects and components. Click each component type to learn more. The VM Home Directory object is formatted with VMFS so that a virtual machine's configuration files can be stored on it. The number of copies of the objects and components that determine the storage availability. The stripe width of the object determines the disk's storage performance. Objects and components can reside on different hosts. When provisioning a virtual machine, if you do not select any other Virtual SAN policy and set the VM storage policy field on the Select Storage page to None, the default storage policy that VMware provides is applied to all virtual machine objects. The following are the characteristics of Virtual SAN default storage policies. The Virtual SAN default storage policy is compatible only with Virtual SAN data stores. The default storage policy is applied when the policy that you assign during virtual machine provisioning does not include rules specific to Virtual SAN. Because the default virtual machine storage policy is compatible with any Virtual SAN data store in the vCenter server, you can move your virtual machine objects provisioned with the default storage policy to any Virtual SAN data store in the vCenter server. You cannot apply the default storage policy to non-Virtual SAN data stores, such as NFS or a VMFS data store. You can clone the default policy and use it as a template to create a user-defined storage policy. You can edit the default storage policy using the ESXCLI command. To edit the policy, you must have the Storage Profile View privilege. VMware highly recommends that you do not edit the settings of the default storage policy. You cannot edit the name and description of the default storage policy or the virtual SAN storage provider specification. All other parameters, including the policy rules, are editable. Note that when you edit a default policy, you should repeat the process on every host in the virtual SAN cluster. You cannot delete the default policy. However, if a user-based policy is created and made the default policy, then the user default policy can be deleted. When you have an application deployed with the required service levels, Storage Policy-Based Management, or SPBM, can be applied to ensure the container can match those requirements for those virtual machine objects. You can apply the policy either to the virtual machine or to the disks individually. Proper use of SPBM and data stores can decrease operating system snapshot intervals. By storing the operating systems and system data separately on different data stores and applying storage policies defining the required service level, snapshot intervals can be decreased for virtual machine operating systems with normal snapshot intervals for data. You can do this at per object level. Note that SPBM is performed from the vCenter server. vSAN-SPARSE is a new type of snapshot on virtual SAN. It is expected to have performance comparable to SAN native snapshots. vSAN-SPARSE takes advantage of the new on-disk format writing and extended caching capabilities of virtual SAN 6.0 in order to deliver an efficient performance. Note that virtual SAN 5.5 snapshots were based on VMFS-SPARSE or redo logs. Virtual SAN has a VM kernel port property named Virtual SAN Traffic. Virtual SAN supports both vSphere standard switches and VMware vSphere distributed switch, with either 1 or 10 gigabit Ethernet or GBE network uplinks. The virtual switch must be uplinked to a single Layer 2 or L2 or Layer 3 or L3 Ethernet broadcast domain that provides connectivity to all hosts in the cluster. The virtual SAN cluster hosts must have a virtual SAN traffic-enabled VM kernel port connected to a virtual switch. For best security and performance, it is recommended to isolate virtual SAN network traffic to its own L2 or L3 network segment. In virtual SAN, a vSphere distributed switch or VDS facilitates the traffic flow across the network. Traffic flows in a virtual SAN network can be monitored either when a virtual machine on a host behaves as a destination machine or monitoring device. The storage I/O traffic always flows through the virtual SAN network. VMware vSphere Distributed Switch simplifies the data center administration by abstracting and storing the configuration of virtual networks in VMware vCenter Server. VMware recommends the use of vSphere Distributed Switch with 10 GBE network uplinks. Faster Ethernet links are favored because of the potential for large amounts of replication and synchronization traffic generated by virtual SAN to saturate a 1 GBE network uplink. When using vSphere Distributed Switch, you can enable the VMware vSphere Network I/O control in order to allocate share values to different types of traffic, and also to mitigate the impact of contention. In a virtual SAN network, multicast protocol should be enabled on the L2 physical network segment utilized for virtual SAN intra-cluster communication. Any host can join a multicast group by using Internet Group Management Protocol, or IGMP. IGMP manages multicast groups using query and report messages. The L2 switches of the virtual SAN network monitor the IGMP query and report messages to find out which switch ports are subscribed to which multicast groups. This functionality of a L2 switch is called IGMP snooping. L2 multicast traffic can be limited to specific port groups by using IGMP snooping. Using the IGMP snooping feature, a network switch can listen to the IGMP conversation and maintain a map. This map provides details about the links needed by the different IP multicast streams. Multicasts can be filtered from the links that do not need them. Thus, the switch can control which ports receive specific multicast traffic. VMware does not recommend the implementation of multicast flooding across all ports. Also, Virtual SAN does not require Layer 3 or L3 multicast, which is now supported in Virtual SAN 6.0 for any of its network communication requirements. If the hosts that are participating in Virtual SAN span across multiple switches or L3 boundaries, the network must be configured in such a way that multicast connectivity is enabled. You can also change the default multicast addresses if required by your network environment, or if you are running multiple Virtual SAN clusters on the same L2 network. Virtual SAN 6.0 supports failure domains by allowing grouping of hosts in a Virtual SAN cluster into different logical failure zones. This ensures that the replicas from a virtual machine are not provisioned onto the same logical failure zones. Failure domains are not metro or stretched clusters. Fault domains provide the ability to group hosts within a cluster and define failure domains. Virtual SAN fault domains ensure that the replicas of virtual machine data is spread across the defined failure domains. A fault domain consists of one or more Virtual SAN hosts grouped together according to their physical location in the data center. When configured, fault domains enable Virtual SAN to tolerate failures of entire physical rack, as well as failures of a single host, storage disk, network link, or a network switch dedicated to fault domains. Fault domains provide the ability to tolerate rack failures, flash and magnetic devices failures, storage controller failures, network failures. Virtual SAN 6.0 fault domains provide the ability to tolerate rack failures and power failures in addition to disk, network, and host failures. If the Virtual SAN cluster spans across multiple racks or blade server chassis in a data center, it is important to ensure that the hosts are protected against rack or chassis failure. This can be achieved by creating fault domains and add one or more hosts to it. When a rack fails, all resources including CPU, memory, and Virtual SAN in the rack become inaccessible to the cluster. To avoid this, you should configure fault domains of smaller sizes. This increases the total amount of resource availability in the cluster even after a rack failure. Virtual SAN 6.0 provides limited support for controller-based checksums to detect corruption issues and to ensure data integrity. Now that you have completed this module, you should be able to describe the architecture of the Virtual SAN 6.0, identify the objects and components of the Virtual SAN 6.0, explain snapshots, clones, traffic flow pattern, and fault domain of Virtual SAN 6.0.